Hello everyone, in this lecture I am going to discuss about the transmission line. So this is the subject of microwave and radar engineering of electronics and communication engineering branch. I will discuss the introduction of this microwave, why it is called microwave. So microwaves are the form of electromagnetic wave which radiates with wavelength ranging from 1 meter to 1 millimeter with frequency 300 megahertz to 300 gigahertz. So microwave includes the entire SHF band. Frequencies in the microwave range are often referred by the IEEE radar band designation LSCXKU, K and K band. So prefix of micro in microwave is not meant to suggest a wavelength in the micrometer range. So rather it indicates that microwaves are small compared to the radio waves used prior to microwave technologies. So this is the microwave. Microwave deals with the communication technology in the frequency range from 300 megahertz to 300 gigahertz, and the wavelength in vacuum ranging from 1 meter to 1 meter. So what is the range of microwave region? 3 gigahertz to 30 gigahertz, and in millimeter wave region from 300 gigahertz to 30 gigahertz to 300 gigahertz. So what will be how will you calculate the wavelength? By using the simple formula, lambda is equal to c by f, where c is the velocity of light and f is the frequency for which you want to measure the wavelength. So this is the frequency spectrum designation which is used which will be used in this microwave. So you can see, and the designated band is written here and with their applications. So this is the IEEE microwave frequency band designation given by IEEE. So this is the old designation and this is the new one. So you can see here, earlier 3 to 4 gigahertz was known as S band, right? We are seeing that this is the G band. Similarly, you can see in this table. What are the advantages of this microwaves? Wide bandwidth, high directivity, small size antenna, low power consumption and effect of fading. So in wide bandwidth, the bandwidth of microwaves is larger than the common low frequency radio waves, thus more information can be transmitted using the microwaves. So it is very good and advantageous because the microwaves are used for point to point communication. So in high directivity at microwave frequencies, there are better directive points and with their properties. This is due to the relation that the frequency increases, wavelength decreases, and as wavelength decreases, directivity increases and beam width also decreases. So it is easier to design and fabricate high gain antenna in microwaves. So as I have already discussed, the small size antenna, so microwave allows to decrease the size of antenna as well as the frequency increases, the size of the antenna decreases. The antenna size can be smaller as the size of the antenna is inversely proportional to the transmitting frequency. Thus the microwave, we have waves of much higher frequencies than the other frequencies. Low power consumption, the power required to transmit a high frequency waves, high frequency signals is lesser than the power required in transmission of low frequency signals. Now the effect of feeding. The effect of feeding is minimized by using the line of sight propagation techniques at microwave frequencies, while at low frequency signals, the layers around the earth causes fading of the signal. So these are the application of microwaves. There are many industry, medical and domestic applications of microwaves. Some are used in communication, non-destructive evaluation, heating and medical sciences. In real life, we are using the microwave oven. So, in communication, microwave is used for broadcasting and telecommunication transmission. As discussed, they have shorter wavelengths and allows to use smaller antennas. Microwaves are also used for transmitting and receiving a signal from Earth to satellite and from satellite to Earth. And remote sensing, most of applications are in radar, and radar is used to illuminate any object by using a transmitter and receiver to detect its position and velocity. Anything microwave oven is used to bake and cook the food. It is very convenient electronic machine which performs the heating task very cleanly and in very less time. And in medical applications, we are using for diagnosis and various therapies. Some other applications of microwaves in personal services and infrastructure medicine and in infrastructure, medical and sciences. Now coming to the transmission line, the classification of transmission line is based on their geometry and electrical mode. So, geometrical we can use multi-conductor or single conductor, and in electrical mode you can say we can use TEM mode or non-TEM mode. The example of multi-conductor is coaxial cable, twin lead line, parallel plate lines and strip line, etc. In a single conductor we are using the waveguides, and in non-TEM modes we are using the TE, TM, HEM, etc. Now what is the TEM mode? I am interested here in the transmission line, so I am going to discuss these modes, non-TEM modes and TEM modes. So what is the transmission line? In the transmission line, what is the TEM mode? So TEM mode is a mode of propagation characterized by electric field E and magnetic field H patterns that are purely transverse with respect to each other and with the axis of transmission line or the direction of the propagation. A transmission line can support TEM mode only if there are at least two disjoint conductors in its cross section and the medium filling the cross section is homogeneous, isotropic and lossless. Now what is TE mode, what is TM mode and what is hybrid mode? TE mode is known as transverse electric mode, TM mode is known as transverse magnetic mode, and HE mode is known as EH or HE mode is known as hybrid mode. So the transverse electric mode, also called H waves, and characterized by the fact that the electric field being always perpendicular to the direction of propagation. In TE mode, the electric field is purely transverse to the direction of propagation and the magnetic field is not purely transverse in nature. In TM mode, this is also called E waves, are characterized by the fact that the magnetic vector is always perpendicular to the direction of propagation. In TE wave only the H field is purely transverse to the direction of propagation of electric field, which is not purely transverse. In hybrid mode, both TE and TM waves are coupled together and are present simultaneously. In other words, we can say that Ez is not equal to 0 and Hz is not equal to 0. So sometimes we are EH or HE, hybrid mode is called EH or HE mode. So what is the appropriate model for this transmission line? A mathematical model gives the cutoff frequencies and the propagation constant for the line if line for low frequency, high frequency and medium frequency. How will you define the range of frequencies, or you can say which is the low frequency, which is the high frequency and which is the medium frequency? So on the basis of this, wavelength, we can classify the low frequency, high frequency and medium frequency. So, if low frequency we are using the lumped element model, in high frequency we are using the field model, in medium frequency we are using the distributed element model. But a transmission line is generally a few wavelengths long, then it is convenient to extend the lumped element model into the distributed element model. So, what is the distributive element model? So, in this transmission line is assumed to be made of a series of lumped elements or distributive elements, where V, voltage and current cannot vary over each incremental length, that is delta Z. So, here I have considered two parallel lines having the length L. Here I have considered a small part of this transmission line which is having the length of delta Z, and here the voltage and current is a function of distance as well as time, length as well as time. In this transmission line model, we are using resistance, inductance, conductance and capacitance. So, these are the primary constant of the transmission line, and the resistance, inductance, conductance and capacitance are unit of these primary constants is ohm per meter, Henry per meter, Siemens per meter and Farad per meter. So, if I want to draw the distributive model for this transmission line, so we have to include this these primary parameters. So, here this resistance and inductance will be in series and this conductance and capacitance will be in parallel. So, here I can write the equation, voltage and current equation, differential equation in terms of this transmission line by applying simple KVL and KCL in this infinite transmission line. So, if I apply the KVL, and KCL, then I will get here voltage is nothing but, this voltage is nothing but the resistance multiplied by the current and inductance multiplied by the delta I by delta T. So, you can see here delta Vz by delta Z, delta V by delta Z is equal to Ri plus L di by dt, or you can write delta V by delta Z is equal to minus Ri minus L di by dt. Similarly, we can write for this delta I by delta Z is equal to minus GV minus C delta V by delta T. So, here I have applied this KVL and here I have applied this KCL. So, we can write here, if I take the Laplace transform of these two equations, so we can write dV by dZ is equal to R plus j omega L I Z. So, this is nothing but this with negative sign. So, here I can also write di by dz is equal to minus g plus j omega c into Vz. Now, similarly we can write gamma and z naught for this. Gamma is nothing but, gamma is the propagation constant and this is the combination of attenuation constant and phase constant, and gamma is equal to alpha plus j beta, and gamma is equal to under root r plus j omega L into g plus j omega c, and this z naught is known as characteristic impedance. Characteristic impedance is given by under root r plus j omega L upon g plus j omega c. Similarly, we can write, after calculation we can convert this into the complex number. So, these propagation and characteristic impedance, this propagation constant and characteristic impedance is known as secondary constant of this transmission line, and for lossless line gamma is imaginary and z naught is real. I will consider. So, how will you find the propagation constant for at microwave frequencies? This is the transmission line, this is the characteristic impedance for the transmission line and propagation constant of the transmission line. So, at microwave frequencies it can be seen that R is less than omega L, G is less than omega C. So we can by using this binomial expression, we can calculate the transmission line, we can calculate the propagation constant and characteristic impedance. So gamma is equal to R plus j omega L, G plus j omega C. Here I have considered that R is less than omega L and G is less than omega C. So I have taken common j omega L from this bracket and j omega C from this bracket. So I will get here j omega square and root LC 1 plus R by j omega L and 1 plus G by j omega C. So we can write here j omega under root LC 1 plus 1 by 2 R j omega L 1 plus 1 by 2 G j omega C by expanding this using the binomial expression. We will get here j omega under root LC 1 plus 1 by 2, we will multiply this. So if I multiply this, I will get here 1 plus 1 by 2 R by j omega L plus G by j omega C. By multiplying here, I will get here 1 by 2 R under root C by L plus G under root L by C plus j omega under root LC. So if I compare this with gamma is equal to alpha plus j beta, then I will get the value of alpha and beta. So what will be the value of alpha? Alpha is nothing but 1 by 2. This is the real part of this gamma. Gamma is equal to 1 by 2 R under root C by L plus G under root L by C. So this is the value of alpha and this is the value of beta. Beta is equal to omega under root LC. Beta is equal to omega under root LC. So I can see here the value of alpha and beta from the propagation constant. For lossless transmission line, gamma is imaginary. So in case of lossless transmission line, attenuation will be 0. So gamma will be equal to j omega under root LC. So what will be the value of characteristic impedance at microwave frequencies? I have already considered that R is less than omega L and G is less than omega C. So the value of this characteristic impedance is Z0 is equal to under root R plus j omega L upon G plus j omega C. So under root L by C 1 plus R by j omega L and 1 plus G omega C 1 plus G by j omega C power minus half. So I will use again the binomial expression for calculating this. So after calculation I will get here Z0 is equal to under root L by C. So lossless transmission line, for lossless line Z0 is real. General expression for this characteristic impedance is Z0 is equal to R plus j omega L upon G plus j omega C. Let us take an example for calculating the characteristic impedance as well as propagation constants. In this question, the transmission line has the following parameters: R is equal to 2 ohm per meter, L is equal to 8 nanohenry per meter, G is equal to 0.5 millimho per meter, C is equal to 0.323 picofarad per meter and F is equal to 1 gigahertz. So you have to calculate the characteristic impedance and propagation constant. So we have to use the general formula for calculation of this characteristic impedance as well as propagation constant, because condition is not given here for we have to calculate for lossless transmission line for or lossy transmission line. So here nothing has been given, so I have to use the general formula of calculation. Now we can consider the transmission line. If the transmission line is terminated with the perfectly matched condition or mismatched transmission line. So we can consider here two cases. When Z0 is equal to ZL, so this is the perfectly matched transmission line. Consider in this case maximum power will be transferred to the load and hence there will be no reflected wave inside the transmission line, and the standing wave pattern will be the combination of incident and reflected wave. So in this case reflected wave does not exist, because in case of perfectly matched conditions the incident wave or the input wave will be absorbed by the load and no wave will be reflected back to the transmitter side. In case 2, when Z0 is not equal to ZL, this condition is known as mismatched transmission line. So there will be reflected wave in the transmission line, and there will be the standing wave pattern, and the VSWR will be voltage standing wave ratio will be a finite value. So now for infinite length transmission line, this is the expression Vz is equal to V and I is travelling in the positive z direction, then the Vz is equal to V naught plus exponential minus gamma z. If I consider alpha is equal to 0, then we can write Vz is equal to V plus exponential minus j beta z. Similarly, we can write the current expression I plus I naught plus exponential e power minus gamma z. If alpha is equal to 0, then I is equal to I naught plus e ki power minus j beta z. We can find the characteristic impedance by using the simple formula R is equal to V by I. So here we have to find the characteristic impedance Z naught is nothing but V naught plus upon I naught plus. So this will give the formula. This is the characteristic impedance of the infinite length transmission line. If the line is terminated with the load resistance ZL, in that case this Vz will be equal to V naught plus e ki power minus j beta z plus V naught minus e ki power plus j beta z. So this is the combination of incident wave and the reflected wave. So if the incident wave is travelling in plus z direction, then the reflected wave will travel in negative z direction. So we can write the voltage and current expression by using the simple formula that I have written here for infinite length transmission line. So this is the Vz is equal to V naught plus e ki power minus j beta z plus V naught minus e ki power plus j beta z, and the current will be equal to I naught plus e ki power minus j beta z. This is travelling in positive z direction, and this wave is travelling in negative z direction, I naught minus e ki power plus j beta z. So in this case, Vz by Iz will not be equal to this V naught plus upon I naught plus. So what will be the value of this characteristic impedance? The characteristic impedance will be different. If I have considered the incident wave with the reference in plus z direction, then the characteristic impedance for the wave travelling in negative z direction will be different from the incident wave. So what is the reflection coefficient if the wave has been in the mismatch condition? So the reflection coefficient is V naught minus upon V naught plus, by considering that the load is at z is equal to 0. So what will be the value of this? So as I have already written here Vz and Iz, so I can write here Iz in terms of V naught and Z naught. So Iz is equal to V naught plus upon Z naught e ki power minus j beta z minus V naught minus upon Z naught, because I have written here Z naught is nothing but V naught plus upon I naught plus is equal to minus V naught minus upon I naught minus. So by using this expression I have written here. So at the load we can find at z is equal to 0. I have already at z is equal to 0, load is at z is equal to 0. So what will be the value of V naught upon I naught? This will be equal to Z naught V naught plus V naught minus V naught minus V naught plus minus V naught minus. So what will be the value of this? ZL is equal to, this is the load impedance, because the load is at z is equal to 0. So this will be the value of ZL. ZL is equal to Z naught 1 plus gamma upon 1 minus gamma. Gamma is nothing but V naught minus upon V naught plus. So V naught minus upon V naught plus is gamma 0 and here V naught minus upon V naught plus is gamma 0. So this is the formula for load impedance in terms of reflection coefficient. So from here we can calculate the gamma load is equal to gamma 0, because we have connected the load at z is equal to 0. So gamma 0 will be equal to ZL minus Z naught upon ZL plus Z naught. So if the load is terminated at any arbitrary point, then we have to consider here in place of z, I have to write here L at particular distance L. So I have written here V minus L is equal to V naught plus exponential j beta L plus V naught minus exponential minus j beta L. So we can calculate here gamma at distance minus L. I will get here gamma 0 exponential e की power minus 2 j beta L. So what will be the reflection coefficient at distance L? Gamma minus L is equal to gamma 0 e की power minus 2 j beta L. So in this way we can calculate the reflection coefficient at z is equal to 0 and reflection coefficient at some distance L. So this is the procedure how can you calculate the reflection coefficient at any point. So this is all about for today. In the next lecture I will continue with this topic. Thank you.